in the universe. So
you are a killjoy.
no, I have good stuff to talk about, not fake stuff.
Okay, all right. I'll accept that.
All right. So, as you know, most forces, perhaps all forces you've ever encountered, as you go to a higher distance, it gets weaker.
Yeah,
like gravity gets weaker. It makes complete sense.
Makes sense. Yeah.
Okay. And it's true with electricity and magnetism, the electric charges.
Yes.
And there are formulas that describe how the force drops off. It turns out to be a 1/r² force. The r is the radius, or distance squared, when it's gravity and electromagnetism. So in other words, if you triple the distance, it's 3, 1/3 is 1/3, square that, you get 1/9. Okay, so that's what 1/r² means.
All right.
So it's 4 times the distance is 1/16.
Okay.
5 times the distance, 1/25 of what it was.
Right.
So it drops off. And so there are things that happen in our lives that represent this fact. Most of our life experience is embedded in forces that drop off.
If you're married for 50 years, then, you probably 50 times less attracted to that person.
There'll be a linear relation.
Yes, it would be. Notice I did not use the R squared.
R squared.
Because that would mean you hate them.
So, there exist forces that get stronger at greater distance.
Ooh.
And there's a poem about love on that very subject.
Oh, God.
Distance makes the heart grow fonder. Yes, that would be such a force. Can you think of a force that increases with distance?
I'm really trying to think here.
Yes.
Something that gets greater.
Yes, but it is so obvious that you're not thinking about it. That's how obvious it is.
Oh,
you ready?
See. Go ahead.
I'll tell you. A rubber band.
Yeah, that makes sense.
Or a spring. So I take this spring and I stretch it.
Okay.
That takes energy. But the more I stretch it,
the more it pulls.
The more it pulls back on me.
Exactly.
Okay, you didn't like leaving the equilibrium spot. So now I press on the spring.
It pushes back still.
The opposite direction.
No matter what you do, it pushes back.
It tries to get back to home base. This is a different kind of force.
Yeah.
And it has a different equation. Force is minus kx. Leave out the k. K is just a constant. X is like your displacement from the equilibrium.
So that's the push or the pull.
And it's minus because it's opposite what you're trying to do. Whatever you're trying to do, it's the opposite.
Man.
I'm trying to push this way. No, you don't.
Look at that.
Bring that sucker back in to where you were. Now watch. If you start at 0 and you try to push this way, it's pulling you back.
Right.
Okay? Now, if you go to negative numbers, the minus to the x.
Minus.
Gets plugged back to the other direction.
Boom. Love it. Love it.
Boom.
Love it. Awesome.
That's the intersection of the math and the physics.
That's math in real world.
Correct.
I love it.
So now watch.
Go ahead.
Let's go back to gravity now. I can toss something and it'll go up, slow down, and turn back around. I have an equation that will describe that. What happens if I displace the spring and let go? It'll do this.
Right.
Because it'll get to the midpoint, it'll overshoot.
And go further.
And
now
then
I'm plus, and then it goes back.
And it goes back.
But then I'll go back.
Welcome to the harmonic oscillator.
Up. Get out.
This is harmonic motion. When is the spring moving its fastest?
Should be when you first let it go, right? No. Oh, no. At the middle.
At the middle.
That's
At
right.
the middle.
Yes, because you pulled it. And now it's static. But now it's accelerating.
Now the force is accelerating it by this new formula.
And then it gets to the middle, but it's no longer. Now it's pushing.
It overshoots.
Dude, I gotta go. That's brilliant.
Okay.
I love it.
Now, there's the force, but then I want to know what it's doing over time.
Right.
There's some equations going to have t in it, time. Okay? So, to solve the harmonic oscillator, you need trigonometry.
Oh, it's been nice.
Is that where you part
That's
ways?
that's where I gotta go, guys. Trig, my worst subject.
Okay, so the vertical axis is where you are. Then the sine curve will take you there on the upside and take you there on the downside.
That actually makes sine curves a little more easy to understand.
Okay, you got that?
Yeah.
It's taking you up and down with it.
Right.
And in calculus, the first derivative of your position is your speed.
Okay.
Now, the first derivative in calculus is just the slope of the line representing where you are. And if the sine curve is where you are, you're first up here, and now you're down here, as time goes on, up here and down here, what is the slope at the top of the curve of a sine curve?
0.
0. Thank you.
Yeah. Okay. Oh my God, I'm doing calculus.
Yes, you are. Yes, you are. So watch. So at the top of the curve, that's when the thing is displaced the most.
Right.
I said the slope, which is the first derivative in calculus, the slope is the speed by definition. So the speed at the top of the curve
0.
is 0. And that's where it's at maximum displacement.
Right.
And in fact, it has to be 0.
Of course.
Because a moment before it was going in this direction.
Exactly.
And the next
now
moment,
it's got to come back. At some point, it's got to stop completely, hit 0, and then boom, now it's accelerating in the opposite direction.
So now in this sine curve, where is the slope the highest? So you have to ask, where is the slope the steepest? Because eventually the slope flattens out again at the bottom.
All right, and becomes 0.
It becomes 0. So where is it when it has maximum speed? It's
in the middle.
In the middle.
In the
which
middle.
we had already established.
Right.
And I'm saying the sine curve, it's built into the features of the sine curve. That's harmonic motion. Harmonic motion is everywhere.
Yes, it is.
You know what it is? It's in a rocking chair.
Right.
When is Grandpa moving the slowest?
Right
at the edge, okay?
I'll tell you. I remember when sine curves weren't even sine curves.
Sine curves were just curves.
They were just curves.
There's no trick.
There ain't no trigonometry tell you about no curves.
So a rocking chair is harmonic motion.
That's harmonic motion.
What else? There's
A
things.
slinky.
Yeah, slinky would be
Slinky,
harmonic
total
motion
harmonic
because it's
motion.
a spring,
It's a
right? So you
spring.
just watch it,
Sweep,
and you just watch it.
Yeah, you just
watch it
yeah,
oscillate.
exactly.
Now it'll eventually slow down and stop because it's friction,
Right.
dissipation of it inside the material.
Inside the spring itself.
But you learn in physics class, you learn the perfect case, a massless spring with no friction, and you will go forever.
Right.
But nothing will really do that. But you get the equations, and later you put in the correction for the friction and the dissipation and the like.
Wow.
This was physics, calculus, trigonometry.
Yeah.
All this.
That's
and
really cool.
harmonic motion. Oh, I got another one for you.
That's so great.
Ooh.
Go ahead.
Ooh.
Go ahead.
A pendulum is harmonic
That's
motion.
harmonic motion.
You want to describe a pendulum? And where's the pendulum moving the slowest?
At the very top.
At the
Either
edges.
end. Either end. Yeah.
And gravity is the force, the restorative force in
Pull
each
it back
direction.
down.
And that's going to have a sine curve in it. In the solution to that equation, a pendulum takes the same amount of time to complete a swing, no matter how wide you swing it.
And this seems very counterintuitive.
Yeah, because it thinks as...
That makes sense. Because the speed changes.
Yes.
So if the speed changes.
Because what happens is the higher up I bring it,
Right.
the more it falls
Right.
before it gets to the bottom.
Exactly. So it's the same amount of time.
Exactly
It's just
the same-
covering more distance in that time.
Because it's moving
because the
faster.
speed's faster.
Correct.
Look at that.
Now, do you know who first realized this?
No, I do not.
Galileo. Being bored in church in a hot summer day, the windows are open. The wind was blowing and the chandelier was swaying. And he noticed that no matter how fast the wind blew and how much it swung, it took the same amount of time
to go to and fro.
And you know how he measured the time?
No.
With his pulse.
See, look at that. Look, put your finger right there, and you got bo, bo, bo. Now you look at the swing. Bo,
And
bo,
it was the same
bo,
each
and
time.
it's the same each time.
So he didn't invent the pendulum clock, but he discovered the fact that the pendulum by the way, if you pull the pendulum too far out, then there are nonlinear effects that will influence it. So we're talking about the linear mode of a pendulum is within a range. Okay.
Yeah.
You just bring it up here. That's
Yeah,
not
now
gonna
that's going to work.
Then it's
Yeah,
all right. You can figure that. You can calculate that. Anyhow, Galileo didn't invent a pendulum clock, but he discovered the fact that a pendulum, no matter how wide its arc, will keep the same time. So if you're going to make a reliable clock
Right.
with something that doesn't vary, put a pendulum in it. Christian Huygens, a Dutch polymath from the 17th century, he figured out that the angle doesn't really matter. It'll keep the same time.
Keeps the same time.
Put the pendulum inside the clock, thus is born the pendulum clock.
Look at
He
that.
has this major work called Horologium Oscillatorium.
Okay.
Horology is the study of time and timekeeping and oscillations, right? So therein is the fundamentals of the pendulum clock. It was the most visible expression of a pendulum.
Did he also put the cuckoo bird in the clock?
That was the Swiss, I think.
Oh, okay. Yeah.
This is harmonic motion. Anytime you see something swaying back and forth, there's a restoring force that gets greater the farther the thing goes away.
dope.
It's totally dope.
That is amazing. I love it.
And this is basic physics. It's not your first week of physics.
It's physics in real life. It's great.
All right, we're done here, Chuck.
That was great.
That's been another Star Talk Explainer on harmonic motion, and it didn't